Hello, everybody. Welcome back to Markov processes. I want to ask you how the homework is going, but first I wanted to get a couple of things out of the way. These are things that appeared in a short-ish 8-minute video that I put in the announcements, but I know not everyone has looked at that. And these things are expectations for the exponential distribution conditional on that exponential random variable being less than a number or greater than a number. We need to do this computation at least twice in the current homework, and we're going to be doing it many more times in the upcoming weeks. So let's get going. Suppose I have a random variable t that is exponential with rate lambda. We do know that the expected value of t is 1 over lambda. But right now, I wanted to look at an expectation like the expected value of t given t is greater than c. This one is actually not so bad by lack of memory. If you look at like a timeline here, and this is, I'm going to put like c right here. And I have the time to the first arrival, so t, which is exponential here. If I know that it's greater than c, then the expected time until I get here is c plus this remaining time, which by the lack of memory property of the exponential is again exponential with rate lambda. So the answer here is c plus the expected value of the same exponential or another exponential, but it has the same distribution, and that is c plus 1 over lambda. Now that's perfectly valid and perfectly mathy, but if you want to know how to do this just a little more formally, to compute the expected value of t such that t is greater than c, you could integrate from minus infinity to infinity t times the PDF for t given that t is greater than c of t dt. We've never actually seen a subscript like this before. We have talked about the conditional expectations, say for a random variable s given another random variable t, in which case you get two arguments separated by the given line. But here there's only one random variable. So what does this PDF mean? The long way would be to go for the CDF, and that would be to look at the probability that t is less than or equal to t given t is greater than c. And then I would use the definition of conditional probability to write this out and go. And then after computing that, I would take the derivative with respect to t of whatever you got, and that would take this conditional CDF into a conditional PDF. I'm going to go somewhere in between our lack of memory argument and this total formality by trying to get you this PDF with a picture. So if t is exponential with rate lambda, then we have a PDF that starts at lambda and goes down exponentially. And this is a t-axis, and this PDF is lambda e to the minus lambda t. But if you have a constant down here and you are conditioning on the random variable being greater than the constant, then what you're doing is looking at the PDF only here, and you don't actually need this part over here. That's gone. We're in the conditional universe where we are up here. The PDF for t, given that t is greater than c, as a function of t, is going to be the exponential PDF. And then to make it so that if we're just looking at this part right here, get another color, we're just looking at this part right here, we want that to integrate to 1. So I want to divide by the area of the shaded region. And this is 1 minus the probability that the regular old exponential is less than or equal to c. That is, it is the tail probability that t is greater than c. That is e to the minus lambda c. So I'm going to divide by e to the minus lambda c. And then note that this PDF is 0 when you are below C. So this is for T greater than or equal to C. That is the same PDF you would get if you went back here and tried to write out the conditional CDF, because that is a probability and we know how to work with conditional probabilities. And then at the end took the derivative. You should end up with this. And finally, if you were to put that PDF next to a T and integrate, and by the way, the limits of integration are going to go from C to infinity because the PDF is 0 otherwise, you should end up with the same thing we got here, C plus 1 over lambda. So let's try to go the other way, which I consider the more difficult way. Suppose we have our T that's exponential with rate lambda, and we want to compute the expected value of T given T is less than or equal to C. So if you go the route of finding the PDF, then it's not really harder or easier than the other case. The thing that makes this a little harder is you can't do that lack of memory trick. So one way to do this would be to figure out the PDF for T given T is less than or equal to C as a function of T. And that means you're going to be looking at the exponential distribution with rate lambda, but only below some number C, which means this part is gone, which means you're using the PDF lambda e to the minus lambda T as long as T is between 0 and C, but it has to be divided by this total shaded area. Once you find that PDF, then you can find this expectation by integrating, in this case from 0 to C of T times whatever you get in that process. I did say that we wouldn't be able to use the lack of memory to make the kind of cleaner argument that we did before, but we do have another option, and that is to look at the expected value of T, unconditional, and write it as the expected value of T given T is less than or equal to C times the probability that T is less than or equal to C plus the expected value of T given T is greater than C times the probability that T is greater than C. So you'll see that what we want is right in here, and we do in fact know all the other pieces. The expected value of T, because T is exponential with rate lambda, is 1 over lambda. The probability that T is less than or equal to C is the CDF evaluated at C. This is 1 minus e to the minus lambda C. This expectation in here, we already worked out. We used the lack of memory and we said this was C plus the expected value of T, which is 1 over lambda. And then finally, this tail probability is e to the minus lambda C. So you can take all these pieces and you can solve for the expected value of T given that T is less than or equal to C, and you can use that in various computations in the current homework. Yeah, for the grad problem or problem 6 on the homework, we do have a Poisson process with parameter lambda, and we have some function g, and we want to know the distribution of the random variable that is the sum as I goes from 1 to the random n of t of g of si, where si are the arrival times, not the inter-arrival times, but the actual arrival times in a Poisson process, S1, S2, S3, etc. If I were you, I would try to get rid of this randomness by conditioning on the value of the process at time n of t. And by the way, since I want the distribution of this and I want to show that it's equal to a similar thing, but with uniforms inside the g, I would start off with the CDF. This is the sum from 1 to n of t, g of si less than or equal to x. And I would condition on the value of the process at time t. So this is going to be the sum from 0 to infinity of the probability of the sum as I goes from 1 to n of t, g of si less than or equal to x, given n of t equals n, times the probability that n of t equals n. So this sum is not going to make sense if n of t, which is n, takes on the value 0, but you can define the sum from 1 to 0 as 0, and you'll be okay. I am going to plug in the given information. This is the sum as n goes from 0 to infinity, the probability, the sum as I goes from 1 to n of g of si is less than or equal to x, given that n of t is equal to n, times the other probability over here, which we know is just a Poisson probability because n of t is a Poisson process. So I have plugged in the n of t equals n, and usually at this point, I argue that you can get rid of the conditional information by independence of the random stuff here and the random stuff here. But we don't have independence because the random stuff on the left side of the conditional line is the S1, S2, S3, etc. And those are the times of the arrivals in the Poisson process. And n of t is the total number of arrivals by time t. So there is a dependence there. But we did show that the times of arrival, so if you fix, let me draw a number line here, time 0, time t, if you know that you have exactly n arrivals by time t, then the locations of those arrivals are just randomly distributed across the interval from 0 to t. They are uniformly distributed on that interval. And we talked a little bit about order statistics. If you let U1, U2 out through UN be IID uniform 0T, then S1 is the same in distribution as the minimum of U1, U2 out through UN. And S2 is the same thing in distribution as the second smallest of the U's, down to Sn, which is in distribution the same thing as the maximum of U1, U2 out through UN. The notation we use for these order statistics is usually one of two things. So U1 in parentheses, U2 in parentheses, out through UN in parentheses, which is different from the original use. And so this is the minimum and this is the maximum, and everything in between is in between. And another common notation is U1 colon n, so like the first out of n, U2 colon n, out through U n colon n. So the distribution of S1 is the same thing as the distribution of this minimum, and the distribution of S2 is the same as the distribution of this second largest one. And so you can replace the S's in here with those order statistics, and you actually don't need to know about the distribution of the order statistics. So let me continue this line down here. This is the sum as n goes from 0 to infinity of the probability of the sum as I goes from 1 to n of g of si, which is now going to be g of ui with parentheses. That's not the ith u, that's the ith u after they're in order. This is less than or equal to x given n of t equals n times the probability that n of t equals n. And these locations of the uniforms are actually independent of this guy, but that's not that important. What is important is you don't know order statistics, most of you in this class, given the prerequisites. So I don't know the distribution of the minimum of the uniform. So if you don't know the distribution of the minimum of uniforms and the maximum of uniforms and everything in between, note that they appear in a sum. And so if I am summing these up, maybe the smallest uniform was actually the sixth uniform in the list U1 through UN. So that will be in there in the sum, but it doesn't have to be in the sixth place. So this is identical to the sum as n goes from 0 to infinity of the probability the sum as I goes from 1 to n of g of ui without the parentheses. So the unordered uniform 0t. And now if you undo the conditioning, you will get back to the probability that the sum as I goes from 1 to n of t of g of ui is less than or equal to x. So we have shown that the original CDF, which is all the way up here, is equivalent to the CDF where you replace the s's by the uniforms on 0 to t. So that's part of that problem. And then you want to find an expectation and a variance. For the expectation, I would condition on n of t again, and I would definitely replace the SIs in that expectation with UIs. And note that the PDF of UI, the unordered UI, is f of t. Let's make this a u. F of u is 1 over t, and this is for u between 0 and t. And it's 0 otherwise. And so you can use that to help you compute the expectation and the variance. And I think the expectation will fall out pretty quickly, and the variance is just a little bit uglier. Okay. I don't know if you have any questions yet, but I wanted to bring one up, and that is problem 4 on the homework, the Marvin the rat problem. What we have is 10 compartments and that in a maze, and that's totally unimportant because there's a food compartment, compartment 6, and someone drops food into that compartment at times of a Poisson process with rate lambda. And it doesn't matter that Marvin knows the maze or not, he can instantly teleport to the food. But when he does that, it's too late because the food has been picked up or eaten by someone else. So the only way he gets food is if he happens to be in that food compartment when the food is dropped. And so if he's somewhere else, he rushes over there, he misses it, and then he will hang out for C units of time, up to C units of time before he gets bored and walks away, and everything sort of starts over again. So we want the expected total time until he gets the food. I'm going to call that W. I'm going to call it a wait, but by this I mean a total time to get food. Okay, so let's let t be one of the exponential rate lambda arrival times. We're going to find what we want to find, the expected value of W, and we're going to find it by conditioning on the value of t. So let's get the expected value of W given t is less than or equal to c times the probability that t is less than or equal to c plus the expected value of W given t is greater than c times the probability that t is greater than c. We know this probability because that's the CDF for the exponential with rate lambda evaluated at c. And we know this tail probability, which is 1 minus what I just wrote down. And what about these other two things? So let's look at the expected value of W given t is less than or equal to c. If he runs to the compartment and just misses out on food, if the time to the next food drop is less than or equal to c, then he'll get it. That doesn't mean he has 0 wait. He has to wait until that food is actually dropped. So this is going to be equivalent to the expected value of t given t is less than or equal to c, because his entire waiting time is just that t given that t is less than or equal to c. As for the other one, the expected value of W given t is greater than c. He is going to start waiting and then he's going to wander away because it took too long. And when the food drops, so that'll be finally at time t, everything is going to reset and start all over. So we actually want the expected amount of time until the food drops, the expected value of t, given T is greater than C. So that's how long it takes for, we already know when T is greater than C, he does not get the food. And this is the time the food will actually drop that he didn't get. And then we're going to start all over with an expected value of W, like a reset. So you will have an expected value of W in here. But to solve for the expected value of W, you just want to combine them and isolate them on one side and solve for the expected value of W. Problem 1b is very similar. It's not exactly the same, but it's pretty similar. So let's do some new stuff. The first thing I want to talk about is the idea of thinning of a Poisson process. So here is the setup. I'm going to suppose that N of T is a Poisson process with rate lambda. And I'm going to classify each arrival or event as either a type 1 or type 2 arrival. And I'm going to do that with probability P and 1 minus P respectively. For what we're about to do, I could easily have 10 different, or let's say K, general K different types of arrivals with probability P1, P2 up through PK, where those P's sum to 1. So this could be 3 types of arrivals or 10 types of arrivals or any other number of types of arrivals. So now I'm going to define or let N1 of T be the number of type 1 arrivals by time T, that's up to and including time T. And I'm going to let N2 of T be the number of type 2 arrivals up to and including time T. Again, we could split this into K different types of arrivals, but my claim is that, I do have to add something to the classification. So I'm going to classify each arrival as type 1 or type 2 with these probabilities and independent of everything else that's going on. I'm just going to say everything to cover all my bases. Like if we have 10 type 1 arrivals in a row, that doesn't mean that the 11th is more likely to be type 1 or type 2. So now my claim is that the process, so now I'm going to put brackets because N of T is just a random variable, but N of T, the collection, is the whole process. So the first process and the second process are independent Poisson processes with rates P times lambda and 1 minus P times lambda, respectively. Or if you had K classes with probability P1, P2 out through PK, where those P's added up to 1, then you'd get K individual Poisson processes with rate P1 lambda, P2 lambda, P3 lambda, and so on. So what we're doing here is we are thinning out the Poisson process. We have some sort of arrival process, a Poisson process, and we are going in and we are flipping a P coin, meaning a coin that comes up heads with probability P and tails with probability 1 minus P. And if we get heads on that P coin, we're going to say we have a type 1 arrival. Maybe that's type 1 and that one and that one, and maybe that one. So if you just consider the yellow circled X's and get rid of the other X's, you have a thinner process. You have a slower arrival rate, and the claim is that it is itself a Poisson process. So there are several parts to showing something as a Poisson process. We have like an I, double I, and triple I from both our definitions. I am just going to show that the number of arrivals by time t for the type 1 process and the type 2 process are independent Poisson random variables with the rates that were given in the claim. So I'm not going to go through all of the type I, double I, triple I. So this is like a partial proof of the claim. I am going to look at the joint probability that the number of type 1 arrivals by time t is some integer n, and the number of type 2 arrivals by time t is some integer m. And what I would like to see is for it to factor into two pieces, and for both of them to be the Poisson type things that we're looking for. The first with parameter lambda p, and the second with parameter lambda times 1 minus p. So to do this, I am going to condition on the total number of arrivals, regardless of type, by time t. I'm going to let k go from 0 to infinity. The probability that n1 of t is n and n2 of t is m, given n of t is some k, times the probability that n of t is some k. But my n and m were fixed at the beginning, so most of these terms are going to be 0 unless n plus m actually is k, because the n of t process is this process plus this process. There's actually only one surviving term here, and that is the k equals n plus m term. So we get the probability that n1 of t is n and n2 of t is m, given n of t is n plus m, times the probability that n of t is n plus m. This is a Poisson probability. As for the other probability, what we have is like some interval from 0 to t, and we know we have a total of n plus m arrivals up to this time. And we want the probability that exactly n of those are type 1 arrivals, and the remaining are type 2 arrivals. So the probability that any one of them is a type 1 arrival is p. And this is a binomial distribution. We have to say out of n plus m total arrivals, you want to choose n to be type 1. The type 1 probability is p to the n, and then we get 1 minus p to the rest, the n plus m minus n, or m. Now, I'm not finished. I still have to deal with this term, but I just wanted to say that if you don't see that binomial there, you can actually write out the definition of this conditional probability and get this in a more, I don't know, mechanical way. I'm not going to say more straightforward, but just conditional probability stuff. I need to multiply by this probability. N of t is a Poisson process with rate lambda, so I get e to the minus lambda t to the n plus m over n plus m factorial. This combination over here is n plus m factorial over n factorial, m factorial, and we do get cancellation of this numerator and this denominator. And as for the rest of it, I am going to pull it apart. I am going to combine things to the nth power, like p to the n and lambda t to the n, to get p lambda t to the n over n factorial. That's almost looking Poisson. In fact, I'm going to take part of this e, and I'm going to take p of that exponent. So I'll get minus p lambda t over here, and then the rest, e to the minus 1 minus p lambda t over here. If you multiply those two e's, you do in fact get this one back. And I have 1 minus p times lambda t to the m. So I took this t and broke it up into the n part and the m part, and some of it went over here and some of it went over here. And finally, this m factorial I can put down here. And you see the two different Poisson distributions. If you've had math stat and you had it with me, you know already that you have independence and you have the two different Poisson distributions. But this was the joint probability for N1 and N2 being N and M respectively. So if you do want the probability that N1 of T is N, you would take all of that and you would sum out the M. You would marginalize out the N2 and you would get this entire thing. And then finally, there's no M here, so you would pull this out. And the remaining thing is a Poisson distribution with a very funky rate. And when you sum that over all M, that part will be 1. So you will get e to the minus p lambda t to the n over n factorial. And if you similarly try to go for the marginal distribution for the type 2 process by summing out the type 1 process, you will get the other part, and you will see that you have the joint distribution that factors into these two pieces, which represent, in this case, the probability of exactly n type 1 arrivals, and in this case, the probability of exactly m type 2 arrivals. So we got our independence from our factoring, and we saw the two individual Poisson distributions because we claimed, starting with a Poisson process and thinning it by talking about different types of arrivals, that you really get lower rate Poisson processes. So we're going to look at an example really soon that uses this thinning method, but I have more to say first. I have a fun fact for you, and that is that the sum of Poisson random variables is again Poisson, and you get to add the individual rates. New rate is the sum of the individual rates. Now, to show this, we need moment generating functions, and we needed them a while back when I claimed that the sum of exponentials has a gamma distribution, and I decided not to drag you through it, and I put that in the video, and it was totally optional. But I don't think I could get away with, we now need it twice. So I want to say something really briefly about a moment generating function. So suppose that x is a random variable, could be discrete, could be continuous. The so-called moment generating function for x, affectionately referred to as the MGF, is, so we can denote this by many things. I like to use a capital M. I like to use a subscript that tells me what random variable I'm talking about, and then an argument. This is usually like a T or an S or a U. I'm going to use a T. It is defined to be the expected value of e to the tx. If x is continuous, this is an integral, and if x is discrete, this is a sum. Let's just look at the continuous case. This would be the integral from minus infinity to infinity of e to the t little x times the PDF for x dx. And some of you may recognize this as like a Laplace transform. Now, if you don't know what a Laplace transform is, that is totally fine. But if you have seen Laplace transforms, you'll remember maybe that there is such thing as an inverse Laplace transform, meaning that if you can compute this moment generating function, which looks like this integral, then you can recover this PDF from the moment generating function. Although if there was a nice formula, I would write it down. It's a really weird infinite sum of things. My point being that if you have two moment generating functions that are the same, and you try to recover the PDFs in both cases, those would necessarily be the same. Which leads us to the exciting fact that moment generating functions uniquely determine the distribution. If you want to show that two random variables have the same distribution, you could show that they have the same PDFs. Equivalently, you could show that they have the same CDFs. And now, equivalently, you can show that they have the same moment generating functions. This is a big leap. Take mathematical statistics, and you'll talk much more about that. But let's go back to our Poisson example. By the way, these are called moment generating functions because they generate moments, whatever that means. I really don't want to go too far off our Markov track, so I don't even want to talk about generating moments. But I have a Poisson random variable, and the moment generating function for x is, I'm going to call it m sub x of t. This is the expected value of e to the t capital X, nice and random. This is the sum because it's discrete. For the Poisson, x goes from 0 to infinity. I get e to the t little x times the probability that x equals x, which is a nice Poisson probability. So we get the sum from 0 to infinity of e to the tx, e to the minus lambda, lambda to the x over x factorial. This is not a Poisson process, just a Poisson random variable with parameter lambda. I am going to pull out the e to the minus lambda, and then I'm going to combine the two things with x exponents to get e to the minus lambda, the sum as x goes from 0 to infinity of lambda e to the t all raised to the x over x factorial. We have two options here. One is to put some things in and compensate for what we put in and make this look like another PDF that sums to 1. Or the other is to recognize the Maclaurin series expansion for e. This is e to the minus lambda, and then the sum comes to e to the lambda e to the t. And if you combine these, you get e to the lambda e to the t minus 1. So that is the moment generating function for a Poisson distribution with parameter lambda. That was quite a long aside to say that the sum of Poissons independent is Poisson. Let's show that right now. Suppose that x is a Poisson random variable with some parameter lambda 1, and y is Poisson with another parameter, potentially lambda 2, and suppose that these are independent. Let's look at the moment generating function for the sum x plus y. Let's give it an argument like t. This is the expected value of e to the t x plus y. And you can multiply and break that up into the expected value of e to the tx times e to the ty. Here I have a function of x only and here y only, and they're independent. So by independence, you can break up this expectation into a product of expectations. And what we have is the moment generating function for x times the moment generating function for y. And that will always be true. That doesn't depend on the Poisson distribution. That's what happens for two independent random variables. If you want to look at the moment generating function of the sum, you get the product of the individual moment generating functions. But right now, let's let the Poisson come in. So the moment generating function for the Poisson with parameter lambda 1 is e to the lambda 1, e to the t minus 1. And the other one is e to the lambda 2 times e to the t minus 1. And we can put those together and get e to the lambda 1 plus lambda 2 e to the t minus 1. And this is the moment generating function for the Poisson distribution with parameter lambda 1 plus lambda 2. It looks like the moment generating function we saw before, but we have this sum here. And because of this fact that moment generating functions completely determine the distribution, if the moment generating function of x plus y has this Poisson distribution, this is enough to say that x plus y has a Poisson distribution with parameter lambda 1 plus lambda 2. That was a long aside. We finished spinning of a Poisson process. And then we had this long aside to figure out why the sum of Poissons is Poisson and what the new parameter should be. And the reason we did that is to talk about something known as the superposition of Poisson processes. This is like summing two Poisson processes. So here's the setup here. I'm going to let, with brackets, n1 of t, with brackets, it means the whole process, and with brackets, n2 of t, be independent Poisson processes with respective rates lambda 1 and lambda 2. I actually could start with 3 independent Poisson processes, or 4, or k of them, but we're going to define a new process, n of t, to be the sum and my claim is that the process n of t is a Poisson process with rate lambda 1 plus lambda 2. And I'm going to call that lambda. So lambda equals lambda 1 plus lambda 2. Let's prove it. I'm going to use definition 1 of the Poisson process. So we've got I. We want to show that n of 0 is 0, but the definition of n of 0 is n1 of 0 plus n2 of 0. And because those are individual Poisson processes evaluated at 0, these are both 0, and we get 0. So we get property I. The second property was the independent increments property. And here's where you look at a few time steps. So I'm going to let T1 be less than T2 be less than T3. And we want to look at n. We want to look at n of, sorry that again. We want to look at n of T2 minus n of T1 versus, so that's a random variable. That's the number of arrivals in the bigger superimposed process between times T1 and T2. We want to compare that to the random variable n of T3 minus n of T2. And we want to show that those are independent. So what you need to do is just write out what these mean. Like this is n1 of T2 plus n2 of T2, and then minus n1 of T1 plus n2 of T1 versus, and you would do something similar with this guy, and then collect the terms so that you have n1 of T2 minus n1 of T1 plus n2 of T2 minus n2 of T1 versus the same thing, but with T3 and T2. So n1 of T3 minus n1 of T2 plus n2 of T3 minus n2 of T2. We want to show that Poisson process definition 1, part double I, holds. That is, we want to show that this is independent of this, and we just rewrote it as this and this. And now this is going to be a little messy. I don't really want to try to formalize this, but because n1 is a Poisson process, this increment is independent of this non-overlapping increment. Because n2 is a Poisson process, this increment is independent of this non-overlapping increment. And because we assumed that n1 and n2 were independent processes, we have, for example, that this increment is independent of this increment, for example. This is independent of this, and when you put all those together, you can say that the entire thing, let's box this off here, is independent of this entire thing. And that's what we were trying to show. So to finish this off, showing that these superimposed or added Poisson processes is Poisson, I want to show that n of some s plus t minus n of s, we want to show that this is Poisson with the given parameter lambda times t, where lambda was defined to be lambda 1 plus lambda 2. So I'm going to let s be anything greater than or equal to 0 and t greater than 0. And if you write out what this is n1 s plus t plus n2 s plus t minus n1 of s plus n2 of s. And reorganizing the terms, we get n1 of s plus t minus n1 of s plus the same thing, but with n2s. So this is a Poisson random variable. It is Poisson with parameter lambda 1, because it's the n1 process, times t, the length of that time interval. And this one is a Poisson random variable with parameter lambda 2, which is the rate for the second Poisson process, times t, the length of the time interval. And we were given that the two processes were independent. And we just showed, using moment generating functions, that when you add two Poisson random variables, because right now this is not a process, this is just a random variable, you get another Poisson, and you get to add those rates. In other words, a Poisson with parameter lambda 1 plus lambda 2 times t. So there's that lambda parameter. You've added the two individual rates. Okay, let's try to use some of the things we learned about today. We're going to have a Poisson bug race. So here is the setup. I kind of have a two-dimensional grid split down the middle lengthwise. 1, 2, 3, 4, 5, 6, 7, 8 with 8 positions. And I'm going to have a bug sitting here. And I'd like to draw a completely different bug over here, but that's the only kind of bug I can draw. So a spidery looking bug, which isn't a bug, but whatever. So this is bug 1 and bug 2, and we have them jumping across this grid, staying in their own lane at times of a Poisson process. They each have their own rate. So bug 1 jumps or hops at times of a Poisson process with some rate lambda 1, and independently, so they're not looking at each other and thinking, oh, I'm getting behind, I must go faster. Independently, bug 2 jumps according to a Poisson process with rate lambda 2. So my first question is, what is the time of the first jump or hop? Well, I don't know the time, it's a random variable. So what is the distribution of the time of the first jump? So if we let B1 be a bug 1 jump time, and B2 be the same thing for bug 2, these are both exponential. Bug 1 has rate lambda 1, and bug 2 has rate lambda 2, and the time of the first jump is the minimum of these two jump times. And the minimum of exponentials is exponential. We've mostly been talking about that for identically distributed exponentials, but we did show it. I went back to check that this is exponential with rate equals lambda 1 plus lambda 2. So we're done with question 1. Question 2, what is the probability that bug 1 is the first to jump? To answer this, I am going to superimpose the two Poisson processes. So I'm going to let n of t be bug 1's process by time t plus bug 2's process at time t. And this is the total number of jumps up to and including time t. We know by the superposition principle that n of t is a Poisson process with rate lambda defined to be lambda 1 plus lambda 2, the individual rates. I want the probability that bug 1 is the first to jump, and this is really at any sort of moment in time, the probability that bug 1 is the next to jump. Let P be the probability the next or first jump is bug 1. So we're assigning bug 1 or bug 2 with probability P and 1 minus P. We can actually thin out the bigger jump process involving both bugs. And we would get that the bug 1 jump process is, did I already have a name for this? I did not have a name for this, is a Poisson process, I guess I don't need a name, with rate equals P times lambda. So that's thinning. We started with superposition, and now we're just picking out one process with thinning. But we know it should have rate lambda 1, i.e. P times lambda, which is P times lambda 1 plus lambda 2, is supposed to equal lambda 1. And if you solve for P, you get lambda 1 over lambda 1 plus lambda 2. So as you're going along, the probability that any particular jump is bug 1 is the relative rate of bug 1 versus the total rate. And the probability that any particular jump is bug 2, that's going to be lambda 2 over lambda 1 plus lambda 2. And in the future, you can just use this as a fact. You don't have to rederive it because you will be asked a similar question to that many times. Okay, my third question, I'm not going to solve, just going to set up. It's very hairy. What is the probability that bug 1 wins? And what does that even mean? So the race is over when one bug hits 8, I don't know if hits is the right word to use, but finishes 8 jumps. If we let like W1, I know it looks like weight, but W is also my favorite word, letter for a gamma distribution, be the total time for bug 1 to finish the race, and W2 to be the total time for bug 2 to finish the race. They each have to hop 8 times, and the hop times are exponential. And when we sum them up, we get a gamma distribution with parameters 8, lambda 1, and another gamma distribution with parameters 8 and lambda 2. And we want the probability that W1 is less than W2. And you can attempt to compute that by conditioning on one of these variables. It's not nice. I don't think you're going to be able to do the integral in closed form, but you could numerically approximate it or something like that. That's why I just said the setup for this problem was the only thing I kind of cared about, not so much actually doing it because it's really, really ugly. But as an alternative method, you could remove time completely because you just care that bug one, we want the probability that bug one wins, and you just want the probability that bug one reaches 8 jumps before bug two. So if you think of, I'm not even going to write this down. You can check it out in the notes if you care, but forget time and just think, what's the probability that there are 8 jumps for bug one and not 8 jumps for bug two. So there could be 8 jumps for bug one and 0 for bug two, 8 jumps for bug one and 1 for bug two, 8 jumps for bug one and 2 for bug two, up to 8 jumps for bug one and 7 for bug two. There's going to be 7 probabilities to add here, and they're going to involve the negative binomial distribution. And we haven't talked about it in this class. I have a feeling this might be like moment generating functions where I try not to talk about it, but then later realize we're going to use it at least one more time. The negative binomial distribution is kind of like the geometric distribution more than the binomial. We had 2 geometric distributions, one where we had independent trials of an experiment with success or failure on any one trial, and little p being the probability of success. And the geometric could count the number of trials up to and including the first success, or the number of failures before the first success. The negative binomial will count, it has the same setup, but it'll count either the number of trials up to and including the rth success, where this is some positive integer, or the number of failures before the rth success. So there's 2 negative binomials and they correspond to the 2 geometrics. And we want the probability of 8 successes for bug one, which is a sum of 8 geometric random variables, which has this negative binomial distribution. So if you care, check it out in the notes where I have worked this example out, but even then I don't give a final answer. I just leave it as a big sum of ugly terms. Okay, so the final thing we can do today is we're on our way to definition 3 of a Poisson process. And I think I've said before that all 3 of these definitions are important in different contexts. You'll use a different definition depending on what you're trying to do. And definition 3 is defined in terms of they're called little o of h functions. So here's the definition. I'm going to take a function f. It's not necessarily a PDF. It's probably not a PDF. It's going to be a function of some letter, say h. And we're going to say this is little o of h if the limit as h goes down to 0, so h is coming down to 0 from the right through positive values, f of h over h is 0. So if that denominator is going to 0, the fraction is blowing up unless the numerator is going down to 0 fast enough to take over. So note that this implies that the limit as h goes down to 0 of f of h is 0. I don't know why I wrote it like that. Let me put this h down here. Not only is f going to 0, but it's going fast enough to counteract something in a denominator that's also going to 0, which could blow up the fraction. As an example, we're mostly going to deal with polynomial type functions. F of h, if it's defined to be h squared, is little o of h. So we write that with a small o of h. And this is true since if you take the limit as h goes down to 0 of f of h over h, you get the limit as h goes down to 0 of h squared over h, which is the limit as h goes down to 0 of h, and that's going to 0, and that's what we needed to get a little o of h function. Notation is, rather than saying f of h is little o of h, instead we write f of h equals little o of h. Point of this is going to be to do rigorous mathematics in a sloppy way. We're going to have Taylor series expansions and things, and we're going to have terms that are really negligible in the sense that they go to zero so fast they can counteract a denominator going to zero. And we're just going to say, oh, that term, that's a little o of h term, and we're going to replace an f of h with a little o of h in various computations that are coming up. So if we are dealing with a polynomial type thing, as long as the power of h is greater than 1, it's going to be little o of h. Here's the thing, or some things. So we use little o of h for many things, many functions. And so one thing we can write is that a little o of h plus a little o of h is equal to a little o of h. What the heck does that mean? It doesn't, you don't put a 2 here. This is representing some function with that limit property. This is representing some function, a different one, with that limit property. And together, if you add them, you'll get a new function with that limit property. And so you just wrap it all up into a little o of h term. So you don't bother with 2 times little o of h. And equivalently, little o of h minus little o of h is not 0 because this is representing some function that has that property. And this is representing most likely a different function. So they're not going to cancel. Instead, little o of h minus little o of h is going to be another little o of h function. But let's prove the one I claimed over here. So I'm going to take an f of h and a g of h, and they're going to be little o of h functions. And I want to look at the sum and whether or not that is little o of h. So I want to look at the limit as h goes down to 0 of f of h plus g of h divided by h. And I can write this as the limit as h goes down to 0 of f of h over h plus g of h over h. And when I take both limits, because f and g are these little o functions, I get something that goes to 0 plus something that goes to 0, and I get 0. And that's how we show that this is another little o of h function, because we took two functions so that if you individually divided by h and let h go to 0, those fractions go to 0. And we saw that if you add them and divide by h and let h go to 0, it still goes to 0. But we write it in this way. Little o of h plus little o of h is another little o of h function. Again, you never want to write like 2 times little o of h, or you never want to cancel a little o of h with another little o of h if you're subtracting, because this and this represent different functions, usually. Another thing in my list, if f of h is little o of h, so we can write that by saying equals little o of h, and c is a constant, then c times f of h is another little o of h function. And to show this, I'm going to take the limit as h goes down to 0 of c, need some room up here, c f of h over h. And that's going to be c times the limit as h goes down to 0 of f of h over h, which by definition is 0. So we get c times 0 or 0. And that's what we needed to show that c times f of h is a little o of h function. I have time to show one more. And that is that a little o of h function times a little o of h function is little o of h. You might get a little lax here and think that everything is little o of h, but it is not true that a little o of h function divided by a little o of h function, this is not necessarily little o of h. And this is easy to see if you think of those polynomials. H cubed is a little o of h function because when you divide by h, you're left with h squared, and that goes to 0 as h goes to 0. And we already saw that h squared is a little o of h function. And when you divide, you just get h. But this is not little o of h, because if you divide h by h, you get 1. And if you then send h to 0, you still have 1, and it's not going to 0. So we don't have every possible way to combine little o of h functions, resulting in another little o of h function, but we do here. So this represents some function like f and some function g, and we want to look at the limit as h goes down to 0 of f of h times g of h over h. Here we only have one denominator. We can't put that under both of them, but that's okay because we have the limit as h goes to 0. Just pick one for the h to go under. This guy goes to 0 by definition of a little o of h function. And this one also goes to 0 because remember, the function itself has to be going to 0 in order to counteract a denominator going to 0. So this is 0 plus 0, which is 0. So we took a little o of h function times another little o of h function, divided by h, let h go to 0, and we got 0. And that tells you that the product is again little o of h. And one more time, we say that symbolically, little o of h times little o of h is little o of h. You don't say little o of h squared usually. These are not the same things. So I am out of time. Next time, I'm going to talk about the quantity e to the minus lambda h in terms of little o of h functions. What we're going to do is write out Taylor series expansion and then classify terms as little o of h. And then we're going to use that for definition 3 of a Poisson process, which has, instead of exponentials or Poissons, it has these little o assumptions, which are assumptions that things are negligible if, say, the interval you're looking at shrinks. So if you have a Poisson process, the probability of having 3 arrivals in an interval is whatever it is, but as the interval shrinks, that probability goes to 0. And in fact, even one arrival in there, the probability will go to 0 as the interval shrinks. But the probability of 2 or more is even more negligible, is going to 0 faster than the probability of one arrival is. So we'll talk about that next time on Markov processes.
Oh no. Hey, where am I? Why are we out here? I don't think stop poking me. I want some leaves. I love squash. Back in the bin. Do you like squash? No, I like squash. Move over. I want some. Yeah. Can I have a potato with that? Yes. I don't know. What? I hear a cow.
Yeah, bitch, I'm a cow. Bitch, I'm a cow. I'm not a cat. I don't say meow. Bitch, I'm a cow. Bitch, I'm a cow. Bitch, I'm a cow. Bitch, I'm a cow. I go moo.
Oh no. Put the light on. I need you to. I see you like squash. I wish you could. Everyone, we're just trying to sleep under here. I don't think she sees us. Oh, I've got a tail. Nobody move. Everybody. Did you see that fish pellet? Freeze. She's getting there. We're good. I don't want to go out there. Stay still. Come on. She doesn't know.
It's a very special friend of mine, my very favorite little pal. Oh, rubber ducky, you're the one. You make bath time lots of fun. Rubber ducky, I'm awfully fond of you. Vo-vo-vo-dee-o, rubber ducky, joy of joys. When I squeeze you.
Hey, who ordered the fish? Oh my god, fish! I love fish. Are you gonna really like fish? Fish are straight by the We're almost like vegetarian. We're crustaceans, you know, and yeah, it's time to lose that extra fish. I would never turn that down. Otherwise, we're eating leaves. Fish. I can't get up. You know, no. Oh, turn over. Hey. Oh, no. I'm getting it. Wait. Okay. So, oh. I'm a duck. I better make a break for it.